Level 0. The ocean floor shifted. Nobody on the surface noticed anything unusual. Hundreds of miles from the nearest coastline, a wave formed, and for a while, it didn't look like anything at all. Ships crossed directly over it and registered nothing. Satellites measured a surface change of less than 1.6 feet, 0.0005 kilometers. To every instrument we had pointed at it, it wasn't there. It registered as nothing. Not a blip, not a footnote in a ship's log. Just open water doing what open water does, which is exactly what made it so dangerous. In 40 minutes, it hit shallow water, and every mile of open ocean it crossed, it was storing energy, compressing it, waiting for somewhere to put it. That somewhere is a coastline, and the people on it have no idea. This is not a tsunami story. Tsunamis you can track, warn against, survive. What we're covering today operates on a different scale entirely. One where the physics stops cooperating with human reaction time, where the wave height stops fitting inside the models, and where the geological record shows us events so large that entire civilizations were erased and nobody alive today knows their name. We start at the bottom of this scale, the smallest megatsunami ever survived by a living person. July 9, 1958. Lituya Bay, Alaska. A fisherman named Howard Ulrich is anchored for the night when he hears what sounds like thunder rolling off the mountains. He looks up. The entire north wall of the fjord is moving, the whole face of it, sliding as one solid piece into the water below. He had 4 seconds between seeing it and the wave reaching him. He survived. His boat rode up and over a wave that stripped every tree off a mountainside at 1,720 feet, 0.524 kilometers above sea level. There was no time to radio for help, no time to think. The wave simply arrived and either you were on the right side of it or you weren't. That's the part that's hard to sit with. Not that it happened, but that this is the entry level, the floor. The thing about a megatsunami that makes it categorically different from a regular tsunami is the mechanism. A regular tsunami spreads energy across thousands of miles of ocean floor, arriving as a long, fast swell, devastating but distributed. A megatsunami happens when something massive and concentrated hits the water all at once. All that displacement at a single point. The wave that comes out isn't slightly bigger. It's a different animal entirely. What Ulrich survived is the bottom of that scale. Everything from here is documented in rock layers, sediment cores, and marine fossils sitting at elevations the ocean has no reasonable explanation for ever reaching. Every level on this list actually happened. But what happens when geography works against you? When the water has nowhere to go except up? That's where the next level lives. And it starts with an engineering decision that probably should have gone differently. Level 1. The Vajont Dam, Northern Italy, 1963. If you haven't heard of this one, that's honestly kind of remarkable given what happened. Engineers building the dam had flagged the mountain slope above the reservoir as geologically unstable. It was in the project documentation before construction even finished. The decision was made to proceed anyway. There were surveys done, arguments made internally, and at some point someone signed off on continuing, and that decision never got reversed. The warning was written down. It existed. Someone read it and kept going. On October 9th, roughly 9.5 billion cubic feet, 0.27 cubic kilometer, of rock dropped into the reservoir in a single movement. The wave cleared the top of the dam by 820 feet, 0.250 kilometers. The dam itself didn't break. It's still standing today, structurally intact. The water just went over it and hit the towns below. Nearly 2,000 people died. There's something about that detail, the dam surviving, that keeps sitting wrong. All that engineering, all that concrete, and it held. It just turned out the dam was never the problem. The problem was the mountain, and the mountain had been telling them that for years before it proved the point. What limits this tier is the same geography that makes it so violent. A confined body of water, a fjord, a reservoir, a bay, focuses all that wave energy in one direction, which is why the heights get so extreme. But the moment it hits the open ocean, the energy spreads and drops fast. A few miles offshore and you'd barely register it. So there is a ceiling here, and it's a geographic one. The confined space is what creates the extreme height, but it's also what contains the damage. Step outside that container, give the wave room to travel, and the rules change. Move that same event to the seafloor, give it hundreds of miles of open ocean with nothing to slow it down, and that ceiling disappears entirely. The problem is that the seafloor has no shortage of unstable slopes, and some of them are a lot bigger than a reservoir wall in northern Italy. Level 2. The largest landslides on Earth are the ones nobody sees. They happen on the edges of continental shelves underwater, after centuries of sediment slowly accumulating past the point a slope can hold, and then the whole face goes at once. In silence, in the dark. No witnesses, no records. Just the aftermath sitting on the seafloor waiting for someone with the right instruments to come along and ask what happened. In 1929, an earthquake off Newfoundland triggered one at the Grand Banks. The way researchers reconstructed what happened was by tracking undersea telegraph cables. They snapped in sequence, one going silent every few minutes as the debris flow overtook them. That sequencing lets scientists calculate the speed, over 60 miles, 96.6 kilometers per hour down the slope, which is fast enough that nothing on the seafloor in its path had any meaningful chance of not being in its path anymore. 28 people died, treated at the time as a serious disaster. Against what the geological record shows is possible, it barely registers. Off Hawaii, ancient submarine slide deposits cover a section of seafloor bigger than Connecticut. Debris blocks the size of small towns traveled hundreds of miles from where they started. If you work backward from the volume of displaced material, the waves those collapses produced arrived at nearby coastlines, several hundred feet tall, and were still 30 to 50 feet, 0.009 to 0.015 kilometers, high at the far side of the Pacific. House-sized boulders sitting on Hawaiian cliff tops at elevations no storm surge could reach. Marine fossils at the same elevations. The evidence has just been sitting in the rock this whole time. Geologists find it, publish papers about it, and the rest of us largely go about our lives without thinking too hard about what it implies. The thing worth noting about all of those Hawaiian slides is what caused them. It wasn't external pressure, it wasn't an earthquake that came along and pushed a slope past its limit. It was the island itself, slowly loading weight onto a foundation that was never going to hold all of it indefinitely. Lava building on top of lava, year after year, century after century, until the whole structure tips past the point it can recover from. A submarine landslide still usually needs something external to push it over the edge. But what if the thing generating the instability is the island itself? That's not a landslide anymore. That's something considerably harder to prepare for, and Hawaii has done it at least 15 times. Level 3. Hawaii has done this at least 15 times. Worth sitting with for a second. 15 documented major flank collapses in the geological history of a single island chain. None of them required an earthquake. None of them required anything external at all. The island simply kept growing until it couldn't hold itself together anymore, and then it didn't. The Nuuanu Slide, somewhere around 1 to 2 million years ago, scattered debris across the seafloor in a deposit the size of Connecticut. Individual blocks the size of Manhattan ended up hundreds of miles from where they started. Simulations of the wave height at the collapse site come out at over 1 mile, 1.6093 kilometers. 1 mile of vertical water moving outward in every direction at once. The number is large enough that it stops feeling like a number and starts feeling like a description of something that shouldn't be physically possible. And yet the debris field is right there on the ocean floor, and it had to come from somewhere. Volcanic islands are basically a structural failure that hasn't finished announcing itself yet. Lava stacks up faster than the foundation underneath can consolidate, groundwater gets in, hydrothermal systems quietly dissolve the interior rock over centuries, and the whole flank shifts incrementally toward a threshold. The process is slow enough that it looks stable from the outside for a very long time. When it crosses that threshold, the collapse takes minutes, not gradual erosion over years, minutes. The Cumbre Vieja volcano on La Palma in the Canary Islands has a western flank that multiple research teams have assessed as potentially unstable under certain eruption conditions. The scientific conversation isn't really about whether a collapse would be catastrophic. The Atlantic coastline directly across from it is pretty well mapped, and the numbers aren't ambiguous. The conversation is about likelihood and timing, which is honestly a less reassuring thing to be debating, because likelihood and timing are exactly the two variables that are hardest to pin down for a system that moves on geological timescales. 1 mile high at the source, still around 100 feet, 0.0305 kilometers, when it reaches the eastern United States. But what happens when the entire interior of the volcano doesn't just collapse but disappears, dropping into a void that opens up beneath it in under 2 minutes? Level 4, August 27, 1883, Krakatoa, 23 square miles, 59.5697 square kilometer of island drops into the sea in under 2 minutes. Around 36,000 people die. Waves hit 140 feet, 0.0427 kilometers, across Java and Sumatra. The pressure pulse from the collapse circles the Earth 4 times and gets recorded on barometers in London. The sound reaches Australia. Sailors thousands of miles away watch their harbors rise and fall for no reason they can explain, hours before any news of what happened reaches them. They had no framework for what they were seeing. The ocean was simply misbehaving, and nobody could tell them why. And then you find out Krakatoa was small. That tends to land hard. About 3,600 years ago, the island of Thera, now Santorini, went through a collapse estimated at 4 to 5 times Krakatoa's energy. The caldera swallowed the center of the island. Tsunamis reached Crete, Egypt, the eastern Mediterranean coast. Destruction layers in Minoan coastal sites date exactly to this period. Some of those sites show evidence of being rebuilt once or twice after earlier damage and then simply not rebuilt again after this. At a certain point, the people who would have done the rebuilding weren't there anymore. The Minoan civilization, one of the most sophisticated cultures in the ancient world at that point, came apart in the decades that followed. Whether Thera directly caused that collapse is still debated, but the timing makes it genuinely difficult to argue the two weren't connected. One geological event may have ended a Bronze Age empire. At that scale, the water doesn't really behave like water anymore. A collapsing magma chamber releases pressure so fast that the ocean above it gets launched rather than pushed. The fluid dynamics turn ballistic. The simulation tools built to handle everything below this level reach their limits pretty quickly here. And the estimates researchers produce vary enough that quoting a single number would be misleading. There are currently around 1,500 potentially active volcanoes on Earth. Several sit on islands. Several have caldera systems that have already done this once. They're monitored not perfectly, not continuously, not with the kind of redundancy you'd want given what an unmonitored failure looks like. And if one goes on an otherwise unremarkable morning, the nearest coastline is not getting a warning measured in minutes. Everything covered so far has needed a trigger. A slope giving way, a flank tipping over, a magma chamber finally emptying. There's always been some violent initiating event you could point to, but the next level doesn't work like that. The trigger is temperature, and it's been running for the last several thousand years already. Level 5, 8,150 years ago. The Storegga Slide. Most people have never heard of it. A section of the Norwegian continental shelf, roughly the size of Iceland, detached from the seafloor and slid into the Norwegian Sea all at once. Around 850 cubic miles, 3,540 cubic kilometer of sediment, just gone. The cause wasn't an earthquake or a volcanic eruption. It was methane hydrates, frozen compounds woven through the sediment that act as structural reinforcement, thawing gradually as ocean temperatures crept upward in the centuries after the last ice age. Nobody triggered it. Nobody pushed it. The ocean just got a little warmer for a little too long, slow warming over a long time. And then a threshold crossed and the floor gave way. The wave hit Norway, Scotland, Iceland, and the Faroe Islands. Tsunami deposits in Shetland sit 65 to 82 feet, 0.0198 to 0.0250 kilometers, above current sea level. Marine microfossils, organisms that only live in the ocean, have been recovered miles inland on the Scottish mainland, sitting inside a sediment layer that simply wasn't there before. You can go find that layer today. It has a name. Geologists use it as a stratigraphic marker, a fixed reference point in the rock record, the same way you'd use a dated coin to establish when a floor was laid. The difference is what the marker represents. Not a construction date, but an afternoon when the seafloor moved and the ocean followed. That evidence is in the ground right now. It has been for 8,000 years. At the time, a landmass called Doggerland connected Britain to continental Europe across what is now the southern North Sea, a low-lying plain where people actually lived and farmed. The Storegga wave likely swallowed large portions of it for good. There's a reasonable argument that one afternoon of seafloor movement drew the geographic line between Britain and Europe that has shaped the last 8,000 years of history on that continent. Two populations that had been continuous became separated. The cultures that developed on either side diverged in ways that are still visible today, all of it downstream of a sediment layer letting go. The methane hydrate formations that failed under Storegga are still present today in the North Atlantic, the Arctic, the Pacific. Ocean temperatures are rising. The researchers who study these systems don't describe them as stable. They describe them as currently stable, which is a meaningfully different thing to say. There was no warning before Storegga, no signal anyone at the time would have recognized as significant. The temperature crept up. The threshold crossed. That's usually the point where the floor gives way. Every level on this list originated on Earth. The last level doesn't come from here. It arrives from somewhere we can barely see, traveling at a speed that makes everything above look like it happened in slow motion. And the last time it happened, there was no one left on the receiving coastline to describe what they saw. Level 6. 66 million years ago, a rock 6 miles, 9.6561 kilometers, wide hit the Yucatan Peninsula at around 45,000 miles, 72,420.48 kilometers per hour. At that point, it stops being useful to compare this to anything else on this list. The impact punched through the crust, vaporized an amount of seawater that's genuinely difficult to state in a way that feels real, and displace the rest outward as a wave measured in kilometers of height at the origin point. Every simulation framework used to produce the estimates above this one doesn't have a working range for inputs at this scale. Chicxulub sits outside it entirely. The math doesn't break down. It just stops having anything useful to say. At Tanis, a fossil site in North Dakota more than 2,000 miles, 3,218.688 from the impact, researchers found fish fossilized mid-motion in sediment that arrived within hours of the strike. Tektites, tiny glass beads formed from rock vaporized by the heat of the impact, were lodged in the gills of those fish. The wave got there while debris was still falling out of the sky. The Atlantic coast of North America received waves somewhere above 330 feet, 0.1006 kilometers tall. The Gulf of Mexico received considerably worse. The tsunami didn't cause the mass extinction. It was one piece of a simultaneous multi-system event. The wave that erased coastlines across an entire hemisphere was, in context, a side effect. The part that sticks with people is that Chicxulub wasn't even especially large by the standards of what this planet has absorbed over its history. It's just the most recent significant impact the geological record has preserved clearly enough to read. There have been larger ones. The planet absorbed those too, in the sense that it's still here. The things living on it at the time made it considerably worse. Researchers currently track thousands of near-Earth objects. Some of them have non-zero impact probabilities on timescales measured in centuries rather than millions of years. The honest version of where that conversation sits is, we've cataloged most of the large ones, we think, probably. And the ones we haven't found yet are the ones we haven't found yet, which is either reassuring or it isn't, depending on how you feel about incomplete inventories of things that end civilizations. The next one is already out there, on a trajectory that hasn't intersected with ours yet. Maybe it never does. Probably it never does. But when researchers talk about impact risk, they don't say impossible. They say the probability is low, and they say it in the same careful way that Storegga researchers say the hydrates are currently stable. Same sentence structure, same careful hedge. And when it does eventually happen, whenever that is, it'll look completely ordinary right up until it doesn't. The ocean will do what it's always done across 4 billion years of being hit, flooded, boiled, and frozen solid. It will move.